Is the true speed of light really exactly the same everywhere in the universe? In the energy filament theory, the real relay limit for light in the energy C slowly changes with the cosmic environment, while the C you measure in any local lab stubbornly stays the same. Textbooks quietly treat C as a sacred fixed number baked into reality. But in this picture, C is more like the fastest beat particular patch of media can handle right now. That beat depends on how tight and hard to squeeze the media is. And that tightness can evolve as the universe itself stretches and relaxes. You already know a softer version of this idea from sound. In air, clap crawls; in water, it moves faster; in steel, it races ahead. Because the stiffer the material, the easier it is to pass the shove along. In this picture, the universe is not empty, it is a stretched energy C. The tighter that C is in some regions, the more quickly it can relay any pattern of motion through that region. Local true light speed is just the extreme version of this idea. The sharpest action relays that a region of the C can support without tearing itself apart. When the C is very tight, that upper speed is high. As the C gradually loosens over cosmic time, that upper speed drifts downward. In earlier episodes, we said that particle properties also slowly evolved with the background tension of the C. Here, we are just looking from another angle and saying that the ceiling for light's relay speed is tied to that same tension. In the early universe, the C was more like a pot of lava-thick soup at maximum boiling. Extremely dense and extremely tight. In that regime, the true light speed could easily have been far higher than the value we infer around Earth today. The catch is that we cannot take a stopwatch to the young universe and time a photon directly. So we have to read time fingerprints in the sky. The most important one is the cosmic microwave background. The almost perfectly even 3 Kelvin glow that wraps the whole sky like a temperature blanket. If you assume that light speed has always and everywhere been exactly today's C, huge regions of the young universe would never have had time to talk to each other before they cooled. There would be no obvious way for them to agree on one common temperature. And this shows up in textbooks as the horizon problem. The usual fix is to bolt on a very brief era of wild inflation, where space itself is said to balloon faster than light for a tiny fraction of a second. That story may turn out to be right. But so far, it behaves more like a patch that rescues the constant C assumptions than like a mechanism we have directly checked in the lab. In this picture, you can flip the logic around and let the media change instead. If the early energy C was wounded far tighter than it is now, the local upper limit on relay speeds, including lighting, could have been much higher. Lights and other patterns would then have had plenty of time to run back and forth across the young universe and smoothed out temperature differences before everything cooled and slowed. The uncanny uniformity of the microwave background stops being a coincidence that needs a special one-off event. It starts to look like exactly what you would expect from a hot, tense medium given enough time to mix. Many famous cosmic coincidences fall into the same category. They only look weird when we force today's static constants onto a universe whose particles, the tension field and maximum relay speed have all been slowly evolving. Once you let those quantities breathe, and accept that both particle properties and the true light speed can drift with the energy C, the picture changes. A lot of the too fast, too neat and too lucky stops being mysterious. It starts to look like ordinary bookkeeping in a changing medium. It is important to stress that none of this breaks relativity in any local experiment. Relativity only demands that whenever you measure light speed in your own freely falling lab, you always get the same C. In this view, that local rules still holds exactly. What changes is the deeper relation between that measured C and the underlying state of the energy C on cosmic scales. In the next episode, we'll stay with this theme and ask why your measurement of light speed is so stubbornly fixed even if the universe's true relay limit is slowly shifting under your feet. Tap follow, share it on New Physics, Clear Universe.